A year ago, a team pointed the James Webb Space Telescope at the most famous patch of sky in modern astronomy and found two faint red dots, just two pinpricks of light, sitting 12 arc seconds apart, glowing only in the longest wavelengths the telescope can see. By every test we've used for the last 30 years to find distant galaxies, those two dots were the most distant objects ever recorded. We're talking light from the first 100 million years after the Big Bang. Older than anything any telescope has ever shown us. Older than the first stars were supposed to be. The team did not publish. They waited a full year, took the same picture again, and watched the two dots slide sideways across the sky. Galaxies at the edge of time do not move. Whatever those two dots were, they were not galaxies. So get comfortable, subscribe if you haven't, and stay with us. Because what they actually turned out to be is sitting closer to Earth than the Pleiades, and it is going to change how you think about the boundary between our own galaxy and the rest of the universe. Let's get into it. Part 1. The image we thought we were looking at. On the night of January 20th, 2025, in a control room far from any of the people whose lives this story will eventually touch, a sequence of commands was uploaded to a spacecraft that orbits a stable point 1.5 million kilometers from Earth. The spacecraft is the James Webb Space Telescope, and on this particular night it had been instructed to point its 18 hexagonal mirror segments in a single coordinated motion at a small, unremarkable patch of sky in the southern constellation Carina. The patch of sky it was looking at was anything but unremarkable, of course. It was the location of the most famous galaxy cluster in modern cosmology, an object that has, for almost 20 years, served as the most direct empirical proof we have that dark matter exists. Astronomers call it the Bullet Cluster. It is the place where, in 2006, a team led by Douglas Clow used gravitational lensing data and X-ray imaging to show that the mass of a colliding pair of galaxy clusters was offset from the gas of the same colliding pair of galaxy clusters in a way that simply cannot be explained without some additional invisible matter holding the galaxies together while the gas slammed into itself and slowed down. The mass was in one place, the gas was in another. The light bending the way it was bending told a story that has, to this day, never been seriously refuted. The universe is mostly made of something we cannot directly see. The Bullet Cluster is the picture you would show someone if they asked you to prove it. What is less famous about the Bullet Cluster, but important for the story we are about to tell, is that it is also one of the most useful natural telescopes in the sky. The mass of the cluster bends the light of every object behind it, magnifying galaxies that would otherwise be too faint to detect, stretching their images into thin arcs and bright spots that astronomers can interpret to read what would be invisible without the lens. So when astronomers want to look at the earliest galaxies in the universe, the ones that formed within the first few 100 million years after the Big Bang, the Bullet Cluster is one of the natural choices to point a telescope at. The cluster does some of the magnifying work for free. The program that was running on the James Webb that January night had a name and a number. It was JWST General Observer Program 4598, and its title was Silver Bullet for Dark Matter. The principal investigators were Marusia Bradac at the University of Ljubljana, Alexei Rytarchik, also at Ljubljana, and Marcin Sawicki at St Mary's University in Halifax. The program was designed to use the Bullet Cluster as a natural lens and to image the field at extraordinary depth in 8 separate wavelength filters, ranging from a filter centered on a wavelength of about 0.9 microns, called F090W, out through filters at 1.15 microns, 1.5 microns, 2 microns, 2.77 microns, 3.56 microns, 4.10 microns, and finally a long wavelength filter at 4.44 microns called F444W. Each filter saw a slightly different slice of the infrared sky, and each was exposed for about 6,400 seconds, a little under 2 hours. By the time the night was finished and the telescope had pointed its mirrors back at its parking spot, the deepest infrared image ever taken of the bullet cluster region was sitting in the spacecraft's data buffer, waiting to be relayed back to Earth. A few days later, when the processed images arrived at the science teams, almost everyone scanning the new data was looking for the same thing. They were looking for galaxies at the very edge of cosmic time. The lensing power of the bullet cluster was supposed to magnify whatever was behind it, and the longest wavelength filters on the James Webb were the ones in which the very oldest galaxies, the ones whose light had been stretched by cosmic expansion across 13.5 billion years, were expected to finally appear. Most of the patches in the field showed exactly what the team expected. There were dozens of background galaxies, some bright, some faint, all visible across multiple filters from the bluer ones to the redder ones. There were foreground stars in the Milky Way, easy to identify because they appear in every filter. There were artifacts to clean up, hot pixels to mask, the usual technical work of preparing an image for science. And then, in one part of the field, 12.8 arc-seconds apart from each other, there were two small, faint red points of light that did not look like anything else in the image. If you have not stood under a dark sky in a long time, and you're picturing 12.8 arc-seconds as some kind of dramatic separation, you should know that 12.8 arc-seconds is approximately the angular thickness of a human hair held at arm's length. Two of these things were near each other in a way that suggested they might be physically associated, or might just be a chance projection. They were both very, very faint. They were both completely invisible in the bluer filters, the F090W, the F115W, the F150W, the F200W. They were not present in the next filter up either, the F277W. One of them, eventually catalogued as bullet BD2, became faintly visible at F277W and brightened toward longer wavelengths. The other, eventually catalogued as bullet BD1, did not appear at all until F356W and then brightened sharply by F444W. They were what astronomers call dropouts. They had dropped out of the shorter wavelength images entirely and only appeared in the reddest filters, and if dropouts behave like dropouts usually behave, that meant something very specific about how far away they were. This is the point in the story where the team, looking at the first epoch of bullet cluster imaging, allowed themselves a particular kind of quiet hope. The two faint red points in the bullet field had exactly the appearance of distant galaxies. They had the dropout signature. They were in the field of a powerful natural telescope. They were faint, which is what you would expect for the most distant galaxies ever seen. And they had a temperature distribution, judging by their broadband colours, that looked consistent with starlight that had been stretched by the expansion of the universe for so long that it had been pulled out of visible wavelengths entirely, and now only showed up in the longest infrared bands the James Webb could reach. If interpreted as distant galaxies, the F356W dropout would correspond to a redshift of roughly 30. The F277W dropout would correspond to a redshift of roughly 20. The current spectroscopically confirmed record for the most distant galaxy ever observed is held by an object called JWST 14-0 at a redshift of 14.32, seen as it was about 290 million years after the Big Bang. A redshift of 30 would mean these objects were seen as they were about 100 million years after the Big Bang. A redshift of 20 would mean about 180 million years after the Big Bang. Both numbers are earlier than any galaxy formation model in widespread use comfortably accommodates. The team had something potentially extraordinary, and they knew it. They also knew that in cosmology, things that seem too good to be true very often are. The James Webb had been operational for 2.5 years at this point, and the community had already had at least one round of JWST broke cosmology headlines, when very early candidate galaxies at extreme redshifts had been reported and then partially walked back, and partially reinterpreted, and partially accepted, and partially still debated. The whole field was in a strange state where the standard model of cosmology, called lambda-cold dark matter, or just lambda CDM, was producing predictions that the data sometimes seemed to comfortably match and sometimes seemed to seriously strain. Into this complicated landscape, the Bradach team now had two new faint red points that, if accepted at face value, would mean some of the most distant objects ever found in any image of any sky. They knew the rules. Extraordinary claims required extraordinary evidence, and they were not yet ready to make any claim at all. What they did next, what they decided to do over the course of the next 12 months, and through a second mission to the Bullet Cluster, would turn out to be the most careful and most patient work in the entire story. But before we get there, before we get to the spectroscopy and the second epoch and the proper motion and the slow understanding that something had gone very strange in the way the universe was speaking to us through these images, we need to spend some time with the method itself. We need to understand how the dropout technique works, why it has been the workhorse of high redshift galaxy searches for 30 years, and what the underlying assumption is that connects object invisible in short wavelengths and visible in long wavelengths to object at the edge of the observable universe. Because the strange thing that is about to happen in this story, the thing that no one was quite ready for, is that the assumption was not wrong. The method works. The two faint red points in the bullet field were genuinely dropouts. They genuinely had the spectral break that distant galaxies have. The trick was that something else, something nobody at the eyepiece had been thinking about, also produces that same break, in that same way, in that same wavelength range, and looks identical to a distant galaxy in every measurement except the one the team was about to spend a year obtaining. Part 2. The Dropout Method and Why It Works. In 1996, in a paper that has now been cited more than 3,000 times, and that quietly reshaped what was possible in observational cosmology, an astronomer named Charles Steidl and 4 colleagues, Mauro Giavalisco, Max Pettini, Mark Dickinson, and Kurt Adelberger, published a short letter in the Astrophysical Journal that introduced what would come to be called the Lyman break technique. The idea was simple. Take an image of a patch of sky in several different filters spanning the ultraviolet and visible range. Look for objects that are bright in some filters and dim in others. Specifically, look for objects that vanish below a certain wavelength but appear cleanly above it. That sharp transition, that drop, is the signature of a distant galaxy. The reason it works has to do with hydrogen. The early universe was almost entirely hydrogen and helium, and even today, more than 13 billion years later, the universe is still mostly hydrogen. The hydrogen atoms scattered through space between us and any distant galaxy do something very specific to the light that passes through them. They absorb any photons whose wavelength is shorter than what astronomers call the Lyman limit, the wavelength of about 912 angstroms, which corresponds to the energy needed to strip the single electron away from a hydrogen atom and ionize it. Photons with wavelengths shorter than that threshold get absorbed by the hydrogen. Photons with wavelengths longer than that threshold pass through. The result is that the spectrum of any galaxy, when you look at it from very far away, has a sharp cliff. Above the Lyman limit wavelength, the galaxy's light is mostly intact. Below the Lyman limit wavelength, the galaxy's light is mostly gone. There is a step in the spectrum, a place where the brightness suddenly drops. For a galaxy nearby, that step sits in the ultraviolet, where most ground-based telescopes cannot easily see it anyway. But the universe is expanding, and that expansion stretches the wavelengths of all the light travelling through it. The further away a galaxy is, the longer it has been travelling, the more its light has been stretched. The Lyman limit, which sits at 912 angstroms when the light is emitted, shifts to longer wavelengths as it travels. At a redshift of 3, a redshift parameter astronomers usually write just as z equals 3, the Lyman break gets stretched from about 912 angstroms in the deep ultraviolet to about 3,650 angstroms near the blue end of the visible spectrum. At a redshift of 7, the break shifts to about 7,300 angstroms into the red end of the visible. At a redshift of 14, it shifts to about 14,000 angstroms into the near-infrared. At a redshift of 20, the break shifts to about 19,000 angstroms. At a redshift of 30, it shifts to about 28,000 angstroms. And at all of those redshifts, the result is the same. There is a sharp transition in the galaxy's spectrum, a wavelength below which the light is gone and above which the light is intact. If you take images in multiple filters that bracket the predicted location of the break for a given redshift, you can look for objects that vanish in the filters below the break and appear in the filters above. That object is, almost always, a galaxy at the redshift you were looking for. Steidl's original paper applied this technique to galaxies at redshift around 3, where the break sits in the near-ultraviolet. Such galaxies came to be called Lyman break galaxies, or LBGs, and the technique became the workhorse of high redshift surveys for the next decade. The Hubble Deep Field, taken in 1995, was full of dropout candidates that the Lyman break technique helped identify. The Hubble Ultra Deep Field, taken in 2004, pushed the technique to redshift 6 and beyond, where the break had stretched into the optical near-infrared. The CANDLE survey, conducted with Hubble between 2010 and 2013, extended the catalogue of dropout galaxies into the hundreds. By the time the James Webb launched in December of 2021 and started taking science data in mid-2022, the dropout technique had been validated in survey after survey on thousands of galaxies across redshift ranges that nobody in Steidl's era could have imagined. It works. When you find a dropout, you're almost always finding a galaxy. The James Webb extended the reach of the technique in the most dramatic way yet. Because the James Webb operates almost entirely in the infrared, with detectors sensitive from about 0.6 microns out to 28 microns, it can see the Lyman break for galaxies at redshifts that no previous telescope could reach. The near-infrared camera on board the James Webb, called NIR-CAM, has a set of broadband filters that astronomers immediately recognized as the perfect tool for dropout work. F090W catches galaxies dropping out at redshift around 7. F115W catches dropouts at redshift around 8 or 9, F150W at around 11, F200W at around 14, F277W at around 20, F356W at around 25 to 30. F444W is the last redoubt, the longest broadband filter where a dropout could mean a galaxy at the very edge of the observable universe. When the Bullet Cluster team examined their first epoch images and saw 2 faint red points appearing only in the very longest filters, they were looking at exactly the kind of object the dropout technique had been built to find. The signal was clean. The spectral cliff was sharp. The colours were consistent with the Lyman break being where it should be, if the objects were at the redshifts the photometry implied. By every standard the technique had used for 30 years, and by every validation it had passed on thousands of previous galaxies, these 2 faint red points in the bullet field had every right to be considered candidates for the most distant galaxies ever observed. What the team also knew, however, was that the technique had a known failure mode. It had been documented in the literature for at least a decade. The Lyman break is not the only sharp transition that can appear in the broadband colours of a faint infrared source. There is another kind of object, a much closer object, that produces an almost identical looking break in almost the same wavelength region, for completely unrelated physical reasons. That other kind of object is a class of failed stars, brown dwarfs of an extremely cool type, in our own galactic backyard. And the deeper and more extreme the James Webb's high redshift surveys had gone, the more often the contamination had started showing up. Heinlein et al. Had published a series of papers in 2024 and 2025 identifying brown dwarfs masquerading as high-Z galaxy candidates in the Jades and Sears deep fields. Langrudi and Yorth had published a paper in 2023 identifying 3 brown dwarfs that had been mistaken for what the field was calling little red dot, active galactic nuclei. The contamination was a known problem. It was just that nobody yet knew how serious the problem was, or whether the most extreme high Z candidates ever found were on the contaminated side of the catalogue or the genuine side. This is the situation in which the bullet cluster team found themselves. 2 dropouts, perfectly cromulent under the standard dropout method, in the lens magnified field of the most famous dark matter image in the sky. They could have published. They could have written a paper claiming the discovery of galaxies at redshift 30 and redshift 20, and let the community sort out the validation. They did not. What they did instead was apply for spectroscopy. And then they did something even rarer in modern astronomy. They waited. Part 3. The 2 dropouts, and what they would mean. To understand exactly what the Braddock team was looking at on those processed first epoch images, you need to first understand what it would mean if Bullet BD1 and Bullet BD2 were what they appeared to be. You need to understand the calendar of the universe. The universe is approximately 13,787,000,000 years old. The figure is from the Planck satellite's 2018 Cosmological Parameters paper, A&A 641A6. The number has been steady through several independent measurements since the early 2010s. The Big Bang is, in this picture, the moment when the universe was at infinite density and temperature, the moment from which time began running forward. The first 380,000 years were the so-called cosmic dark ages, a hot opaque plasma of free protons, electrons and photons in which no light could travel any meaningful distance, because every photon was immediately scattered by the surrounding charged particles. At about 380,000 years after the Big Bang, the universe had cooled enough for the protons and electrons to combine into neutral hydrogen atoms. The photons were no longer scattered by free charges, and the universe became, for the first time, transparent. The flash of that moment is what we see today as the cosmic microwave background, redshifted from its original temperature of about 3000 Kelvin to its current temperature of about 2.725 Kelvin. After that flash, the universe entered another dark period, this time called simply the Dark Ages, in which the neutral hydrogen filled space but had not yet been reionized, and had not yet begun forming stars in any significant numbers. The first stars are believed to have formed somewhere between 100 million years and 200 million years after the Big Bang. Models of the very first generation of stars, what astronomers call population 3 stars, suggest they were enormous, hot, short-lived objects made entirely of hydrogen and helium, because no heavier elements existed yet. The first galaxies, assembled from clusters of these stars, are believed to have formed roughly 300 million to 500 million years after the Big Bang. The current spectroscopically confirmed record for the most distant galaxy ever seen is JWST Z14-0, observed by JWST and reported in 2024 by Stefano Carniani and his collaborators at a redshift of 14.32. That galaxy is being seen as it was when the universe was about 290 million years old. Just behind it sits a candidate called MOMS-14, reported by Rohan Naidu and collaborators in 2026, also at a redshift of approximately 14. These confirmed and near-confirmed galaxies sit at universe ages of about 290 million years. They are already, by the standards of pre-JWST galaxy formation models, somewhat surprising. They are brighter and more abundant than expected, and the field has been working hard to understand whether that brightness is because of unusually efficient star formation, unusually dust-free stellar populations, or some other physical effect. A paper by Aaron Young, Rachel Somerville, and Vahang Iyer in 2025 argued that the lambda CDM cosmological model is not actually broken by these observations, that the apparent abundance of bright early galaxies can be accommodated within model uncertainty if you're careful. But the room is tight. The community is watching. Now consider what Bullet BD1 and Bullet BD2 would mean if accepted at face value as galaxies. Bullet BD2, the F277W dropout, would correspond to a galaxy at a redshift of approximately 20. The universe at that redshift was about 180 million years old. That is more than 100 million years earlier than the current confirmed record. It is in the territory where galaxy formation models, even after being stretched as far as they can go, do not really have a comfortable answer for how a galaxy could be bright enough to be seen, even with the magnification of a foreground cluster. Bullet BD1, the F356W dropout, is even more extreme. At a redshift of approximately 30, the universe was about 100 million years old. That is the time frame of the very first stars in cosmological models. There should not yet be a galaxy. There should be, at most, individual luminous objects with masses of a few hundred to a few thousand solar masses scattered across an otherwise dark and neutral hydrogen sky. Anything that is bright enough to be detected, even with lensing magnification, even with the deepest JWST imaging ever attempted, would be an object well outside the comfort zone of every galaxy formation model in widespread use. If the team had been able to confirm these two objects as genuine high-Z galaxies, the paper would have been one of the most consequential publications in modern cosmology. It would have, in plain language, broken the standard model of early galaxy formation. Every theory of how galaxies assembled in the early universe would have needed to be rewritten. The lambda CDM model would have been forced to accommodate either much more efficient early star formation than any current simulation suggests, or some entirely new physics, or some unanticipated mechanism for producing bright structures in the first 100 million years of cosmic time. The implications would have been enormous. The headlines would have written themselves. The Bradach team understood this. They also understood that the implications were exactly the reason they had to be careful. The history of cosmology is full of dramatic-looking results that turned out to have ordinary explanations. The early reports of inflation gravitational wave signals in 2014, for example, by the BSEP collaboration, turned out to be mostly contamination from dust in the foreground Milky Way once the Planck satellite data was used to subtract it. The early reports of stripe pattern excesses in dark matter direct detection experiments have, several times, turned out to be calibration issues. The history of strong claims in cosmology that are later revised quietly is long. Anybody who has spent more than a few years in the field develops an instinct for the kind of result that demands extraordinary patience before extraordinary publication. The Bullet Cluster team had that instinct. They also had a specific named worry. They knew about the brown dwarf contamination problem. By early 2025, the field had already begun developing an uncomfortable awareness that very cold brown dwarfs in our own galaxy could mimic the spectral colours of high redshift galaxy candidates in JWST broadband photometry. Heinlein et al. Had published their first JD's brown dwarf candidates paper in 2024, identifying objects in the deepest JWST extragalactic surveys that turned out, on follow-up, to be cold local stars rather than distant galaxies. Langerudi and Yorth had identified 3 brown dwarfs in 2023 that had been confused with what the field called Little Red Dot AGN. Bergasser and collaborators had announced 7 cold and distant brown dwarfs from JWST's Rubies program. And, most importantly for the Bullet team's particular worry, there was Kappa Tauro. Kappa Tauro is a nickname the field had given to a particular dropout candidate found by Marika Gandolfi and her collaborators in the Cosmic Evolution Early Release Science Survey, a JWST program that had imaged a small patch of sky in Bootes. The object's formal catalogue designation is CEERSU100588. The nickname came from a small mountain in the Apennines, with the appropriate sense of an obscure but striking peak that the team kept coming back to. Kappa Tauro had a photometric redshift estimate of approximately 32. The universe at that redshift would have been about 90 million years old. If real, Kappa Tauro would have been by far the most extreme high-Z galaxy candidate ever found, twice as far back in time as the confirmed record holder, in a region of the cosmological calendar where galaxies should not yet have been able to form at all. The discovery paper, Gandolfi et al. Vessen, Archiv 2 502.02637, had been published in February of 2025. The team had been openly skeptical of their own interpretation. They had explicitly raised the brown dwarf possibility as an alternative. The community had been waiting for follow-up data. The Bullet team knew Capitaro. They knew the Hainline contamination work. They knew that the deeper JWST went and the more candidates the surveys produced, the more important it became to verify any extreme high Z candidate with multiple independent observational tests. So when they saw Bullet BD1 and Bullet BD2 in the first epoch imagery, they did not write a paper claiming the most distant galaxies ever seen. They did something different. They applied for spectroscopy on JWST's near-infrared spectrograph, and they began planning a second epoch of imaging. The thing they were planning to test for with the second epoch was something a galaxy at the edge of the observable universe absolutely must not show. They were going to look for sideways motion. They were going to look for proper motion, and if they found it, the entire interpretation of these two faint red points would change in a single measurement from the most distant galaxies ever seen to objects right here in our own galactic neighborhood, hiding in plain sight, drifting slowly through the disk of the Milky Way while pretending to be something else entirely. They did not know yet what they would find. They had a year to wait. Part 4. Capitaro, the predecessor problem. To really understand why the Bullet team chose patience over publication, we need to spend some time with Capitaro. We need to understand what had already happened to the field's previous most distant galaxy candidate, and why the lessons of that case were sitting in the back of every careful astronomer's mind by the time Bullet BD1 and Bullet BD2 showed up. The Sears survey, which produced the Capitaro discovery, was one of the earliest large JWST programs to image a deep patch of extragalactic sky. The acronym stands for Cosmic Evolution Early Release Science. The program was led by Stephen Finkelstein at the University of Texas at Austin, and it took data in the Bootes part of the sky throughout the second half of 2022 and into 2023. The field is a small one, only about 100 square arc minutes, but it was imaged in 9 different NIRCam filters and partially observed with NIRSpec spectroscopy as well. The Sears catalogue became, for many high-Z surveys, one of the first places to test the dropout method at the deepest redshifts the James Webb could reach. Buried inside that catalogue, at the celestial coordinates right ascension 14 hours, 19 minutes, 32.97 seconds, and declination plus 52 degrees, 47 minutes, 52.11 arc seconds, sat a faint red point of light that the Padova-led team of Marica Gandolfi, Giulia Rodigiero, Marco Castellano, Adriano Fontana, and colleagues had identified during their reanalysis of the survey's longest wavelength filters. They had given it the catalogue number U100588 in the Sears internal naming system. The object had an apparent magnitude in the F444W filter of about 27.68, faint but detectable. It had a non-detection in every filter below 3.5 microns. And between the F356W filter and the F444W filter, the brightness jumped by more than 3 magnitudes. That's a factor of more than 15 in light intensity across less than 1 octave of wavelength. It was the sharpest dropout signature in the entire Sears catalogue. If interpreted as a galaxy, U100588 had a photometric redshift estimate of approximately 32. The error bars were broad, as is always the case with photometric redshifts based on only a few filter detections, but the central value was striking. Universe age at redshift 32, given the Planck cosmological parameters, comes out to approximately 90 million years after the Big Bang. That is 200 million years earlier than the current confirmed spectroscopic record holder. It is well inside the era when, according to galaxy formation models that have been calibrated against the entire previous body of observational data, individual stars might exist, but galaxies bright enough to be seen across that distance simply should not. Gandolfi and her collaborators had a choice to make, similar to the choice the Bullet team would face 2 years later. They could have published the candidate as the most distant galaxy ever found. They did something more measured. They wrote the paper carefully, identifying the object as either a record-breaking high redshift galaxy or, alternatively, a closer-by dust-obscured galaxy at much lower redshift, or, alternatively, an ultra-cool brown dwarf in the Milky Way disk. They titled it deliberately to acknowledge the ambiguity. The arXiv preprint posted on February 4th of 2025 was called Ultra-High Redshift or Closer By Dust-Obscured Galaxies, Deciphering the Nature of Faint, Previously Missed F200W Dropouts in Sears. They presented the data, they acknowledged the three possible interpretations, and they made it clear that follow-up observations were needed. The follow-up came over the next year. The team obtained additional imaging from Sears and from neighbouring JWST programs. They reanalyzed the photometry. They consulted with brown dwarf specialists on the spectral templates available for Y-class brown dwarfs. They worked with Andrea Ferrara on the alternative hypothesis that U-100588 could be a pair instability supernova, a very massive primordial star that had detonated at moderate redshift around 15 and was being seen as a transient point of light. They worked with Kevin Hainline's group on the systematic brown dwarf contamination question. By the time the definitive analysis appeared in Astronomy and Astrophysics in early 2026, as paper A and A706A364, the title had become starker. It was simply Mysteries of Capoturo, investigating the puzzling nature of an extreme F356W dropout. The nickname had taken hold by then. The paper laid out in careful detail the case for and against each of three interpretations. The case for the galaxy interpretation was that the photometric fit at redshift 32 was technically consistent with the data, that the lensing magnification from a nearby foreground galaxy could account for some of the brightness, and that the JWST instrument was sensitive enough that detecting a single bright galaxy at that redshift was, while extraordinary, not physically impossible if the universe was sufficiently efficient at making early stars. The case against the galaxy interpretation was the redshift of 32 would put U-100588 outside the comfort zone of every galaxy formation model, and that the only well-fit galaxy template at that redshift had an absolute ultraviolet magnitude of negative 21.5, which would correspond to a stellar mass that should not yet exist. The case for the brown dwarf interpretation was that Y-class brown dwarf atmospheric templates, specifically the Sonora Cholla and Atmo 2020 model grids, produced extremely good fits to the photometry. The fit suggested a Y2 or Y3 brown dwarf at an effective surface temperature between 300 and 400 Kelvin, sitting somewhere between 127 parsecs and 1,800 parsecs from Earth. The probability of detecting a Y2 brown dwarf in the Sears volume was approximately 2.2%. The probability of detecting a Y3 was approximately 0.9%. The probabilities were small but not absurd, especially given how many candidates the survey had produced and how systematically the contamination problem had begun appearing in JDs and Sears. The case for the pair instability supernova interpretation, developed by Ferrara and by another team led by Myungwon John, was that a primordial massive star between approximately 140 and 260 solar masses would detonate at the end of its short life in a kind of explosion that did not leave a remnant behind. The unstable pair production of electron-positron pairs in its core would cause it to lose pressure support and collapse, then ignite a runaway thermonuclear reaction that would tear the entire star apart. The resulting light curve would have a characteristic shape, with a long slow decline over weeks to months. If U-100588 was such an event at redshift 15, the cosmological time dilation would stretch the light curve to years, and the spectral peak would shift toward the long wavelength filters where it was actually observed. The Gandolfi A&R paper did not pick a winner. It laid out the evidence for each interpretation, noted that the photometric fit at redshift 32 galaxy was the worst of the three by chi-squared, and that the Y-dwarf and pair instability fits were comparable, and called for spectroscopic follow-up and proper motion measurement. The crucial constraint they could provide was a proper motion upper limit from a 2.3-year imaging baseline they had assembled by combining several JWST observations of the field. That upper limit was approximately 0.137 arcseconds per year. At a distance of 100 parsecs, a Y dwarf would typically move at 50 to 100 milliseconds per year. At 1000 parsecs, the same Y dwarf would move at 5 to 10 milliseconds per year. The Sears upper limit was consistent with a brown dwarf, anywhere from about 100 parsecs out to about 1800 parsecs. It was also, of course, consistent with a stationary extragalactic source at any distance. The measurement was, in itself, ambiguous. What the community needed was a proper motion detection or non-detection at much higher precision. Kappa Tau was the case study sitting in everybody's mind when Bullet BD1 and Bullet BD2 appeared in the Bullet cluster imagery in January of 2025. The Bullet team knew exactly what they were looking at. They had two new dropouts in a different field. They had similar broadband colours. They had potentially the same ambiguity. The most distant thing in the picture might also be the closest thing in the picture. That was the phrase that began circulating in the team's internal discussions, half metaphor and half active suspicion. The most distant thing in the picture might also be the closest. The phrase would come back later. For now, it was a kind of working principle. Until proven otherwise, the Bullet dropouts could go either way. The team applied for JWST near-spec time. They got it. The follow-up spectroscopy was scheduled for March 27th of 2025, 2 months after the first epoch of imaging, and then, for the much more decisive test of proper motion, they applied for a second epoch of near-cam imaging through a separate JWST program led by Seiji Fujimoto and Dan Ko, called the Venus program, JWST Go 6882. The second epoch was scheduled for January 21st of 2026, 1 year and 1 day after the first. The baseline they would get would be exactly 1.003 years. That would, if everything went as planned, allow them to measure the proper motion of Bullet BD1 and Bullet BD2 to within a few milliseconds per year. That precision would be enough to settle the question definitively. So they waited. They did the careful, slow, patient work that high-stakes astronomy actually requires. They did not publish anything beyond a brief conference talk at the American Astronomical Society meeting in early 2025, in which they acknowledged the candidates and explicitly declined to commit to an interpretation. They wrote draft papers in 2 versions, one assuming galaxy interpretation and one assuming brown dwarf interpretation, so they would be ready when the data arrived. They followed Kappa Tau's parallel story closely. They spoke at workshops with Heinlein's group about the contamination signatures the JD's surveys were finding. They watched the broader literature. Part 5. The Year of Waiting. The near-spec spectroscopy of Bullet BD1 and Bullet BD2 was obtained on the night of March 27, 2025, using the PRISM mode of the instrument's microshutter array. The PRISM mode is a low-resolution spectroscopy configuration that gives you the entire wavelength range of NER spec, from about 0.6 microns to about 5.3 microns, in a single exposure. The resolving power is modest, only about 100 at most wavelengths, which means the spectra would not show fine atomic or molecular features in detail, but they would show the overall shape of the spectrum, the rough location of any spectral breaks, and the broad absorption bands that distinguish different astrophysical objects from each other. For 2 faint dropouts whose primary need was simply to determine whether the spectral energy distribution was consistent with a galaxy at redshift 20 or 30, with a brown dwarf at a few hundred Kelvin, or with something else entirely, the PRISM mode was the right tool. The spectra came back within a few weeks of the observation. The reductions were straightforward, the calibration standard, the data quality good. When the team examined them, the news was mixed. The signal was clear. The shape of each spectrum was visible. The wavelength range covered exactly the region where any high redshift galaxy break or any cool brown dwarf methane absorption would show up, and the fits when applied to both candidates, told a complicated story. Either interpretation was consistent with the data. The brown dwarf fits had slightly better chi-squared values. The galaxy fits were not ruled out. By the end of the spring of 2025, the near-spec spectra had moved the team's internal confidence away from the galaxy interpretation and toward the brown dwarf interpretation, but not decisively. They needed the proper motion test, so they waited. The summer of 2025 went by. The team worked on other projects. They watched JDs and Sears publish more brown dwarf identifications. They watched Heinlein's group publish the case study of JD's GSBD9, a T5 to T6 brown dwarf at a distance of about 2 kiloparsecs, with a measured proper motion of 20 plus or minus 4 milliseconds per year, in a paper that appeared on Archive in mid-July as preprint 2407.08781. The case study was important because it demonstrated that JWST could measure proper motions at the millisecond level over a multi-year baseline, that the proper motions of nearby brown dwarfs were detectable, and that the cross-check between spectroscopy and astrometry could conclusively identify a contaminant. Fall came. The Sears team published the definitive Capataro analysis paper in A&A. The photometric fit favoured brown dwarf over galaxy and over pair instability supernova, but with overlapping uncertainty regions. The Archive preprint 2509.01664 was submitted in early September. The published version appeared in February of 2026. The community read it carefully. The Bullet team noted that Capataro's situation was about to be tested by the same kind of multi-epoch imaging they themselves had scheduled. The waiting room of astronomy in early 2026 was a peculiar place. Several extremely consequential results were all going to land within a few months of each other. The winter came. The Bullet team prepared the analysis pipeline for the second epoch imaging. They wrote the astrometric registration scripts. They calibrated the expected systematic errors. They modelled the precision they would achieve given the brightness of the targets, the angular resolution of NRCam, the available reference stars in the field. They expected to measure proper motion at a precision of approximately 3 to 10 milliseconds per year. If the objects were galaxies, the measurement would yield 0. If they were nearby brown dwarfs, the measurement would yield tens to hundreds of milliseconds per year. There would be no ambiguity. The result would be decisive. The second epoch NeoCam observations took place on January 21st, 2026, one day after the calendar anniversary of the first epoch. The pointing was identical. The filters were identical. The integration times were matched. The data came back within a few days. The pipeline ran. The astrometric registration was completed. The proper motion measurement was performed. Imagine the moment. A small office at the University of Ljubljana or a laboratory at the University of California, Davis, late on a winter afternoon. The processed images from the second NeoCam epoch are sitting in a window on a screen, beside the first epoch images from a year earlier. A team member, perhaps a graduate student, perhaps a postdoc, opens both files in the same coordinate frame and aligns them on the reference stars. The two faint red points in the field, the ones that had launched a year of careful waiting, are visible in both images. A simple visual inspection is enough to begin the answer. The team member moves the cursor from the position of bullet BD1 in the first image to the position of bullet BD1 in the second image. The cursor moves a small but visible amount. It is the kind of motion you would never see with your naked eye, the kind of motion that takes the angular resolution of the world's most powerful infrared telescope to detect at all. And yet, there it is. The dot has moved. 49 milliseconds across the sky in 12 months. The position the cursor settles on is the kind of position that no galaxy at the edge of the observable universe can occupy on the back of 1 year. Galaxies, even nearby ones, do not move detectably. Galaxies at the edge of cosmic time, with their light travelling toward us for nearly the entire age of the universe, would have proper motions of effectively 0. The team member moves the cursor to bullet BD2. it has also moved 24 milliarc seconds, less, but still unambiguously different from zero. Both motions are roughly in the same direction, about 20 degrees east of north. The angular separation between the two objects has barely changed. The two faint red points in the bullet field are moving together. They might be a wide, co-moving binary, or they might be a chance projection of two unrelated brown dwarfs at similar distances. We do not yet know, but we do know now, with no further ambiguity, that these objects are not at the edge of the universe. The thing at the edge of the universe was not at the edge of the universe. The thing at the edge of the universe was inside the Milky Way galaxy the whole time, drifting slowly across the sky on a baseline measured in years, with sideways velocities of about 116 kilometers per second for the brighter object, consistent with the kinematics of the Milky Way's thick disk. They had been here all along, hidden in plain sight inside one of the most carefully studied fields in the sky, masquerading as the most distant galaxies ever observed, because the spectral break they produced in our broadband photometry happened to fall in exactly the same wavelengths as the Lyman break of redshift 20 and redshift 30 galaxies. Whatever the team member said, whatever the postdoc thought, whatever Marusha Bradash and her collaborators did over the next few days as the results solidified, the universe had spoken. Two faint red points in the bullet cluster field were not at the edge of cosmic time. They were inside our own galactic neighbourhood, drifting through the disk, and the question of what they actually were could now be answered with confidence by combining the proper motion result with the near-spec spectroscopy that had been sitting in the team's drives for 10 months. The brown dwarf interpretation, which had been holding by a thread on chi-squared, suddenly had no competition. There was nothing else this could be. The thing at the edge of the universe was a teacup temperature-failed star. Part 6. Spectroscopy and the methane fingerprint. To understand what the team found when they re-examined the near-spec prism spectra of bullet BD1 and bullet BD2 with the proper motion result in hand, we need to spend some time with a peculiar coincidence in physics. The coincidence is the reason this entire story happens in the first place. It is the reason the dropout method, which has been right thousands of times for 30 years, was about to be wrong for these two particular objects. The coincidence is that two completely unrelated kinds of objects, one at the start of cosmic time and one in our own galactic backyard, leave essentially the same fingerprint in low-resolution broadband photometry. The fingerprint, in the case of a high redshift galaxy, is the Lyman break. We discussed this earlier. Neutral hydrogen in the intergalactic medium between the galaxy and us absorbs every photon with a wavelength shorter than the red-shifted Lyman limit of about 912 angstroms in the galaxy's rest frame. The result is a sharp cliff in the spectrum, a wavelength below which the galaxy is essentially dark and above which it is roughly as bright as it should be. For a galaxy at redshift 20, the cliff sits at about 19,000 angstroms, or 1.9 microns. For a galaxy at redshift 30, the cliff sits at about 28,000 angstroms, or 2.8 microns. JWST broadband photometry samples the spectrum at multiple discrete wavelengths, and a galaxy at redshift 20 or 30 will be detected in filters above the cliff and undetected in filters below it. The fingerprint in the case of a cool brown dwarf is something completely different. A brown dwarf is a small, cool object, intermediate between a planet and a star in mass and in temperature. The very coolest known brown dwarfs, in the Y class, have effective surface temperatures between about 250 and 500 Kelvin. At those temperatures, the atmosphere of the brown dwarf is dominated by molecules, not atoms. Methane, water vapour, ammonia, hydrogen sulfide and carbon dioxide are all present in significant abundances. Each of these molecules has characteristic absorption bands at specific infrared wavelengths. Methane has a particularly strong absorption band near 3.3 microns and another near 8 microns. Water has strong absorption near 1.4 microns, 1.9 microns, 2.7 microns, and longer wavelengths. The combined effect of all these molecular absorptions is to carve the brown dwarf spectrum into distinctive shapes, with regions of relatively high emission separated by deep absorption troughs. For a Y-class brown dwarf at 300 to 400 Kelvin, the shape of the broadband spectrum has a particular feature that turns out to be very important for our story. The combination of water and methane absorption shortward of about 3 to 4 microns dramatically suppresses the brown dwarf's brightness in the near-infrared. The same brown dwarf emits much more brightly at longer wavelengths, between about 4 and 5 microns, where the absorption bands have a relative gap. The result is a spectrum that rises sharply between the suppressed shorter wavelengths and the higher emission at longer wavelengths. The rise looks, to the standard tools astronomers use to identify galaxy candidates from broadband photometry, almost identical to the Lyman break of a high redshift galaxy. It is in the same wavelength range, it has the same general shape. In low-resolution photometry, the two are essentially indistinguishable. When the Bullet team fit their NER-spec prism spectra of Bullet BD1 and Bullet BD2 with a range of candidate models, the brown dwarf templates fit slightly better than the high redshift galaxy templates. The fits used a software pipeline called UCD-MCMC, applied to the ELFO-WL25 model grid developed by Adam Bergesser and others. For Bullet BD1, the best fit effective temperature was 350 Kelvin, with an uncertainty of plus 110 and minus 80 Kelvin. The chi-squared per degree of freedom was 1.3. For Bullet BD2, the best fit effective temperature was 410 Kelvin, with an uncertainty of plus 110 and minus 50 Kelvin. The chi-squared per degree of freedom was 0.9. By comparison, the Galaxy template fits had chi-squared values of 1.4 for Bullet BD1 and 1.2 for Bullet BD2. The brown dwarf fits beat the Galaxy fits, but only modestly. On chi-squared alone, the team could not have committed to the brown dwarf interpretation. They needed the proper motion test. Now that they had it, the brown dwarf interpretation became the only viable one. The chi-squared was confirmatory, not decisive. The proper motion result was decisive. To translate the temperatures into something a human can feel, 350 Kelvin is about 77 degrees Celsius, or 171 degrees Fahrenheit. That is the temperature of a cup of tea that has been sitting out on a counter for a few minutes, slightly cool to the touch, still warm enough to be unpleasant if poured on your skin, but a long way from boiling. 410 Kelvin is about 137 degrees Celsius, or 278 degrees Fahrenheit. That is closer to the temperature of a slow oven, well above the boiling point of water, but not yet hot enough to bake a loaf of bread. These were the surface temperatures of the brown dwarfs that the world's most powerful infrared telescope had been trying to interpret as galaxies at the dawn of cosmic time. The most distant thing in the picture was the temperature of a teacup. There is something about that fact that should give us pause. Two completely unrelated physical processes, in two completely unrelated kinds of objects, in two completely unrelated parts of the universe, are leaving the same fingerprint in our best data. Hydrogen blanketing of starlight from a galaxy 90 million years after the Big Bang. Methane and water absorption in the atmosphere of a failed star 1600 light-years away, in our own galactic backyard. These are not similar processes. They share no physical mechanism. The hydrogen blanketing is an atomic process operating across cosmological distances on light that has been travelling for 13.5 billion years. The methane and water absorption is a molecular process operating in a stellar mass atmosphere on light that has been travelling for 1600 years. The two have nothing in common except that they both happen to produce a sharp spectral transition in the same wavelength range. And, by an accident of physics that nobody chose and nobody planned, the wavelengths happen to match. The high redshift galaxy break and the cold brown dwarf methane break are accidental homonyms in the language of the universe. This is the moment in the story when something quietly shifts. The two faint red points in the bullet field, which the team had been treating as a puzzle to solve, become instead a question to sit with. The universe is speaking in a language that contains accidental homonyms, and our best instruments cannot tell them apart. The boundary between near and far, the boundary between the dawn of time and our own galactic neighbourhood, is not as clean as the textbooks have always suggested. The two unrelated objects produce indistinguishable fingerprints. There is no method failure here. The method works exactly as designed. The problem is that two completely different kinds of objects with no shared physics leave indistinguishable signatures in the data the method is built around. The accident is in the physics itself, not in the technique. If you sit with this for a moment, the implication is heavier than it sounds. What it means is that some fraction of the most extreme, high redshift galaxy candidates that have ever been catalogued in any deep field with any instrument may not be galaxies at all. They may be cold, local brown dwarfs that happen to share the spectral fingerprint. The Bradach team's bullet cluster result was not a one-off discovery. It was a particular instance of a more general property of the universe and of the limits of the kind of measurements we know how to make. What had always seemed to be a clean separation between the distant past and the local present, in the sky, turns out to be slightly fuzzy. Some fraction of what we have been calling the first galaxies are nearby failed stars wearing the same spectral mask. The mask is not deceit, it is geometry, it is chemistry, it is the accidental architecture of how nature has chosen to absorb light at certain wavelengths in two completely unrelated physical situations. The team carried this thought into the rest of the analysis. They wrote the paper. They published it on ARF as preprint 2604.23668 on April 26th of 2026. The title was direct. Two exciting high redshift galaxy candidates turn out to be two exciting ultra-cool brown dwarfs. The implication was clear. They were calling not only their own result but also Capitaro, and by extension a fraction of the high Z literature, into careful question. The community responded by largely accepting the bullet result and by accelerating the proper motion follow-up campaigns on every other extreme high Z candidate that could plausibly be a contaminant. The cleanup is still underway in 2026. What sits in the spectroscopy, what the methane fingerprint really tells us, is that the universe is not failing to communicate with us. It is communicating in a language that occasionally uses the same word for two completely different things. Our job as listeners is to learn the difference. The proper motion test is one way we have learned to do that. The full resolution spectroscopy, when it eventually becomes available for objects this faint, will be another. The brown dwarf community has been quietly building the templates that will eventually let us identify any Y-class brown dwarf in any JWST broadband photometry by combining colour information across multiple filters with sophisticated atmospheric models. The cleanup is methodological. The lesson is broader. The closest thing in the picture and the farthest thing in the picture, by an accident of the underlying physics, look the same. Until we have done the work to tell them apart, we should not assume we know which is which. Part 7. What a Y-dwarf actually is. To really understand what was sitting in the bullet field, what the team had been chasing for a year, and what turned out to be hiding in plain sight, we need to spend some time with the object itself. We need to spend some time with what a Y-class brown dwarf actually is, because the answer is one of the strangest categories of object in modern astronomy, and the chances are good that you have not yet had a chance to picture one clearly in your mind. A brown dwarf is, in the most direct sense, a failed star. Stars form by the gravitational collapse of cold interstellar gas clouds, mostly hydrogen, with a smaller amount of helium and a tiny fraction of heavier elements. As the cloud collapses, the gravitational potential energy converts to heat. The central temperature rises. At some critical mass, somewhere around 75 to 80 Jupiter masses, the core gets hot enough and dense enough for sustained hydrogen fusion to ignite. The new star begins burning hydrogen in its core and stabilizes on the main sequence, where it will spend the next millions to billions of years converting hydrogen to helium and shining steadily. The Sun is one of these stars. Every star you can see in the night sky is one of these stars, with the exception of the very few stellar remnants and supergiants that occupy other regions of the stellar evolution diagram. A brown dwarf is what happens when the gravitational collapse stops just short of that threshold. The gas cloud is too small. The central temperature does not quite reach the value needed for sustained hydrogen fusion. The object that forms still has a great deal of internal heat accumulated from gravitational collapse, but it has no nuclear engine to replace what it radiates. So the brown dwarf cools. Over millions to billions of years, it gives off its heat to space, dimming as it ages, slowly settling toward thermal equilibrium with the cold interstellar medium around it. The boundary between brown dwarfs and very low-mass stars sits at about 75 Jupiter masses. The boundary between brown dwarfs and very massive planets sits at about 13 Jupiter masses, which is the threshold for brief deuterium fusion in the early phases of the object's life. The International Astronomical Union has adopted this boundary as the working definition. Objects above 13 Jupiter masses fuse deuterium briefly in their youth and are called brown dwarfs. Objects below that mass never did and are called planets. The boundary is somewhat arbitrary, and there is an active debate about whether formation pathway should matter more than mass, because objects can form either by collapse of an interstellar cloud or by accumulation in a protoplanetary disk around a star. The deepest JWST surveys are starting to find free-floating planetary mass objects in young star clusters, like the Trapezium cluster in Orion, where Pearson and McCaughrean reported in 2023 the discovery of more than 500 free-floating planetary mass candidates, many of them in apparent binary pairs, in the same RCIV preprint 2.310.01231. The boundary between brown dwarfs and free-floating planets is, in 2026, an unsettled question. The classification scheme for brown dwarfs follows their decreasing temperature with a letter sequence that runs M, L, T, Y. The M dwarfs are the coolest real stars, with surface temperatures from about 2,500 to 3,700 Kelvin. The L dwarfs, introduced by Davy Kirkpatrick and collaborators in the late 1990s in their paper in the Astrophysical Journal, volume 519, page 802, occupy temperatures from about 1,300 to 2,400 Kelvin. The L class is mostly populated by very low-mass stars near the hydrogen-burning limit, and by hot young brown dwarfs that have not yet had time to cool below their formation temperatures. The T class, characterized by strong methane absorption in the near-infrared, was first identified by a team led by Adam Bagassa in 2002. T-dwarfs sit between about 500 and 1,300 Kelvin. They are unambiguously brown dwarfs, not stars, and their atmospheres are dominated by methane in the same way Jupiter's atmosphere is dominated by methane. The Y class is the coolest known category of brown dwarf, with effective temperatures below about 500 Kelvin. The class was officially defined by Michael Cushing and collaborators in 2011 in RCIV preprint 1108.4678, based on a sample of cool objects discovered by NASA's Wide Field Infrared Survey Explorer called WISE. The defining spectroscopic signature is ammonia absorption in the near-infrared, which becomes prominent at temperatures below about 500 Kelvin and is absent in T-dwarfs. The Y class is split into subclasses Y0 through Y2 and beyond, with progressively cooler temperatures. The coldest known brown dwarf is WISE-J, 085-5-0714, often called just WISE-0855, discovered by Kevin Luhman in 2014, and characterized further in subsequent papers through 2024. Its effective temperature is approximately 250 Kelvin, that is approximately negative 23 degrees Celsius, or negative 9 degrees Fahrenheit. It is cooler than the freezing point of water. It is the temperature of a deep freezer. It is the lowest known surface temperature of any free-floating object beyond the solar system. It sits only about 7 light-years from Earth, in the constellation Hydra, making it one of the closest known objects beyond the planets and the Sun. The cooling timescales for brown dwarfs are slow because the heat capacity of degenerate gas is small and the radiating surface area is large. A 30 Jupiter-mass brown dwarf takes approximately 5 billion years to cool below 500 Kelvin and approximately 10 billion years to reach 300 Kelvin. The universe is only 13.75 billion years old. So a brown dwarf at 300 Kelvin today is essentially a fossil of an early Milky Way star formation episode. It has been cooling steadily for 10 billion years, since a time when the Sun did not yet exist and the Earth had not yet been formed. The cool brown dwarfs in our galactic neighbourhood are, in a real sense, the oldest objects we can study at close range. Each one is a small dim record of the conditions in our galaxy's youth. Now picture the surface of bullet BD1. If it had a clearly defined surface, which it does not in the same way a rocky planet does, but if you could find yourself standing somewhere on what passes for the boundary between the atmosphere and the deeper interior of the brown dwarf, what would the experience be like? The atmosphere above you would be dense and grey-brown. The dominant molecules are methane and water vapour, with smaller amounts of ammonia, hydrogen sulfide and carbon dioxide. The methane gives the atmosphere a slight brown tint at certain depths. The water condenses into clouds of ice crystals at the cooler upper layers in the way water condenses into clouds on Earth, but at temperatures and pressures far different from anything in our familiar atmosphere. The ammonia, at the cold tops of the atmosphere, condenses into thin streamers of ammonia ice, drifting slowly in atmospheric convection currents. The sky above you is dark because there is no nearby star to light it. Bullet BD1 is alone, drifting through interstellar space, with no host star to orbit, no sun to give it warmth, no sky of clouds lit from outside. The only light comes from the brown dwarf itself, glowing dimly in the infrared from the residual heat of its long cooling, slowly radiating that heat away into the cold dark around it. The temperature on your skin, if you could somehow be there without the crushing gravity of an object somewhere between Jupiter and Saturn in size but more massive than either, would be about 350 Kelvin. That is approximately 77 degrees Celsius. It is the temperature of a slightly cooled cup of tea, just warm enough to be unpleasant if it touched you. The atmosphere would feel warm and humid, almost tropical, but in a sealed dark room rather than under any familiar sky. The gravity beneath you would be intense, several times Earth gravity, holding you firmly against whatever passes for the surface. You could not stand. You could not move. You could feel the warm gas around you and the dim infrared glow from below, and you could feel the cold dark above you, and you could feel the slow pulse of convection cells circulating the heat upward and the colder material downward. There would be no horizon in any familiar sense. There would be no sun. There would be no civilizations. There would have never been one. This object has been cooling, alone, drifting interstellar interstellar space for 10 billion years. It is older than the Earth. It is older than the Sun. It will continue cooling for another 10 billion years until the temperature drops below 200 Kelvin and the methane begins to freeze out of the atmosphere as snow, and the atmosphere itself begins to thin and chill toward eventual rigid stillness. After that, the brown dwarf will continue cooling for billions more years into the deep future of the universe, long after the Sun has become a white dwarf and Earth has been engulfed. This is what was sitting in the bullet cluster field. Not a galaxy from the dawn of cosmic time, not a structure of billions of stars assembled in the first 100 million years of the universe. Something far stranger and much closer. A failed star, drifting alone through the disk of our own galaxy, 1,600 light-years from Earth, cooling slowly toward the eventual cold of the cosmic background, casting its dim infrared light across space toward the James Webb. The same object, by another set of coincidences, just happens to have a spectral signature that resembles the red-shifted Lyman break of the most distant galaxies imaginable. From the outside, in our broadband photometry, The two look almost identical. From the inside, they have nothing whatsoever in common. Part 8. The deeper population. How many of these are there? The Bradach team's bullet cluster result was striking because it identified two specific brown dwarfs in a specific field. But the deeper question raised by the result was about the population. How many of these objects are there, really, in our own galaxy, hiding in deep JWST fields, masquerading as candidate galaxies at the edge of cosmic time? The answer to that question has been emerging through a parallel research program, conducted mostly through the JD survey, the JWST Advanced Deep Extragalactic Survey, led by a team including Kevin Hainline at the University of Arizona. JD's is one of the most ambitious deep field campaigns ever attempted, covering the Goods South and Goods North fields to depths that no previous extragalactic survey has reached. The primary scientific goal is to characterize the population of galaxies in the first billion years of cosmic time. A secondary and unintended outcome has been to identify a substantial population of brown dwarfs in our own galaxy, hiding in the same fields. In their 2026 analysis paper, Archive 2510.00111, titled JADES, an abundance of ultra-distant T and Y dwarfs in deep extragalactic data, Hainline and his collaborators reported the identification of 41 brown dwarf candidates in the two Goods fields alone. Of these, 31 were classified as T dwarfs and 10 as Y dwarfs. The T dwarfs were found at distances ranging from a few hundred parsecs out to 5 or 6 kiloparsecs, which corresponds to a substantial fraction of the diameter of the Milky Way disk. The Y dwarfs, being colder and dimmer, were necessarily closer, with distances ranging from 100 parsecs out to about 2 kiloparsecs. The team introduced a Bayesian fitting tool called NIFTY for systematically distinguishing brown dwarf spectral energy distributions from those of galaxies. The implication of these numbers, when scaled up to the entire sky, is substantial. The Y dwarf surface density in the JD's depth fields is approximately 0.02 per square arc minute. The T dwarf surface density is approximately 0.1 per square arc minute. There are about 150,000 square arc minutes in the entire sky. Extrapolating these surface densities suggests there are something on the order of 3,000 Y dwarfs and 15,000 T dwarfs, detectable down to JD's depth magnitudes across the whole sky. The total population of Y dwarfs in the Milky Way, including the ones too faint to detect with current instruments, is almost certainly in the tens of millions or hundreds of millions. The total brown dwarf population, across all subclasses from late L through Y, is likely comparable to or greater than the population of low-mass main-sequence stars. This is a remarkable fact when you sit with it. The Milky Way is in part a galaxy of failed stars. The objects we have catalogued as stars over the past 2 centuries are only the visible tip of a larger population, much of which has been cooling quietly for billions of years, scattered throughout the disk, dim enough that no pre-JWST telescope could detect more than a few of the closest ones. The objects astronomers call brown dwarfs are not a small curiosity at the bottom of the stellar mass function. They may be the most common kind of stellar mass object in the galaxy. The standard textbook picture of a Milky Way containing 100 to 400 billion stars may need to be updated to account for an additional population of objects that did not quite make it to stellar status but exist in comparable numbers. What does this mean for our story? It means the Bullet BD1 and Bullet BD2 were not isolated discoveries. They were not lucky finds in one particular field. They were a property of our galaxy, revealed for the first time by the depth and the sensitivity and the proper motion capability of the James Webb. They are typical, not exceptional. There are almost certainly thousands more like them sitting in JWST deep field catalogues right now, waiting to be identified through patient follow-up. The Hainline Group's NIFTY tool and the Bradach team's combined spectroscopy plus proper motion approach are starting to allow systematic cleanup of the High-Z catalogues. The cleanup is ongoing. The fraction of High-Z candidates that are actually brown dwarfs is being refined as more follow-up data comes in. Current estimates put the deep field contamination at approximately 0.1%, which sounds small until you realise JD's alone has produced tens of thousands of candidates. Even a 1 in 1,000 contamination rate means tens of mistaken identifications across the deepest extragalactic surveys. The bullet cluster brown dwarfs are the most spectacular example so far. They are not the only example. They are not the last. Part 9. The dropout method examined. What we have just seen, when we look at it carefully, is the dropout method being audited honestly in real time. The method works. It has worked for 30 years. It has identified thousands of high redshift galaxies through Hubble Deep Field, Hubble Ultra Deep Field, CANDLES, GOODS, JADES, SEERS, and a dozen other programs. The Lyman break technique is not broken. What we have learned is that the method, like all astronomical techniques, has an edge case, and the edge case in this particular instance is the population of cold local brown dwarfs whose spectral signatures happen to overlap the Lyman break signatures of objects at the dawn of cosmic time. Charles Steidl's original 1996 paper, the founding document of the technique, did not anticipate this failure mode. It did not need to. The galaxies Steidl was looking for were at redshift around 3, where the Lyman break sits in the near ultraviolet, far away from any wavelength region where a brown dwarf would be a serious contaminant. The brown dwarf class had not even been fully classified yet. The L class was introduced in 1999, the T class in 2002, the Y class in 2011. The systematic study of brown dwarf atmospheric spectra at the temperatures relevant to the contamination problem only became possible with Ys in 2009 and 2010, and with JWST starting in 2022. The contamination problem could not have been seriously studied before the data existed. As the dropout method moved to higher redshifts over the decades, the wavelength range of the predicted spectral break shifted into the infrared. By the time JWST started looking for galaxies at redshifts 10, 15, 20 and beyond, the predicted break sat in the same wavelength range where cold brown dwarf methane and water absorption produces a similar-looking transition. The collision was inevitable. The first papers documenting the contamination began appearing in 2023. Lasse Langerudi and Jens Jorth published their identification of 3 brown dwarfs masquerading as NIRCam-selected highly reddened AGN, Arcshift 2 308.10900, in the Astrophysical Journal Letters that year. Heinlein and collaborators published their foundational brown dwarf candidate paper for JDs and SEERS in 2024. Adam Bagassa's Rubies program in 2024 announced 7 cold and distant brown dwarfs identified as galaxy contaminants. The Heinlein 2025 paper, 3 brown dwarfs masquerading as high redshift galaxies in JWST observations, Arcshift 2 501.16648, took a closer look at the systematic prevalence of the contamination. The team analysed 14 high-Z galaxy candidates from JDs and SEERS that had been observed with ENIA-SPEC follow-up spectroscopy. 3 of the 14 turned out to be brown dwarfs. The team estimated the contamination rate at approximately 0.1% of deep-field high-Z candidates overall, with the rate rising significantly for the most extreme candidates and for fields at low galactic latitudes where the brown dwarf population is denser. The case study of JD's GSB-D9, a T5 to T6 brown dwarf with effective temperature of about 800 to 900 Kelvin at a distance of about 2 kiloparsecs, was presented in detail. The brown dwarf had a proper motion of 20 plus or minus 4 milliseconds per year, which corresponded to a transverse velocity of about 214 kilometers per second, consistent with thick disk or even halo kinematics. The object had originally been catalogued as a candidate galaxy at redshift around 12. What these systematic studies have revealed is that the dropout method, applied to the deepest JWST extragalactic surveys, is producing 2 kinds of answers from the same fingerprint. One answer is the real high redshift galaxies, which the technique has been correctly identifying for 3 decades. The other answer is the cold brown dwarf contaminants, which the technique has been silently misidentifying because the underlying spectral physics happens to produce indistinguishable signatures in low-resolution broadband photometry. The phrase, 2 answers from the same fingerprint, is a useful way to think about the problem. It is not a flaw in the method, it is a property of the universe. 2 kinds of objects exist that, at this level of spectroscopic detail, look the same. The job of the method, and of the astronomers using it, is to add the additional cross-checks that distinguish the 2 answers. The cross-checks that have proven most useful are proper motion, high-resolution spectroscopy, and combined photometric fits that explicitly include brown dwarf templates alongside galaxy templates. Proper motion is the most decisive because it is fundamentally an astrometric measurement rather than a spectroscopic one, and the 2 physical situations make completely different predictions. A galaxy at redshift 20 must have 0 detectable proper motion. A brown dwarf at 500 parsecs will have tens of milliseconds per year. The 2 cannot be confused once the measurement is made. High-resolution spectroscopy is decisive when it is available because it reveals the molecular absorption features of the brown dwarf atmosphere, the methane, the water, the ammonia, the hydrogen sulfide, that are absent from a high-redshift galaxy spectrum which would show ultraviolet stellar continuum and possibly emission lines from young massive stars. The 2 have nothing in common at high resolution. The problem has only been the low resolution of broadband photometry, where the differences average out into the same-looking spectral break. The community has been incorporating these cross-checks systematically. Every new high-Z candidate worth confirming is now being followed up with a near-spec at higher resolution where possible. Multi-epoch imaging programs are being scheduled to enable proper motion measurement on the most extreme candidates. Bayesian fitting tools that explicitly compare brown dwarf and galaxy templates, like the Nifty tool from Heinlein's group and the related UCDM-CMC framework from Bagass's, are being adopted as standard. The dropout method itself has not changed. The cross-checks around it have, and the high-Z catalogues of 2025 and 2026 are slowly being cleaned up, with a small but non-zero fraction of previously claimed early galaxies being reclassified as nearby brown dwarfs. There is something quietly admirable about this process. The community has not denied the problem. It has not buried the inconvenient reclassifications. It has instead published them openly, including the most spectacular cases, even when those cases involve walking back previously claimed records. The Bradach team's paper, 2 exciting high redshift galaxy candidates turn out to be 2 exciting, ultra-cool brown dwarfs, is exactly that kind of honest correction. The title itself is a statement of method. The exciting galaxy candidates were genuinely exciting. They turned out to be brown dwarfs. The brown dwarfs are also exciting, perhaps even more so, because they represent a hidden population of failed stars in our own galactic neighbourhood that no previous telescope could have systematically identified. The story has not become smaller because the galaxies turned out not to be galaxies. The story has become differently large. Part 10. Kappa Tauro, Return to. We need to come back to Kappa Tauro now, because the story of the bullet cluster brown dwarfs is incomplete without it. Kappa Tauro is the case where the same question is still open. Kappa Tauro is the case where the proper motion test that decisively settled Bullet BD1 and Bullet BD2 has not yet been completed, and where the community is still waiting for the data that will decide between the brown dwarf interpretation and the alternative interpretations that remain on the table. Kappa Tauro is what the bullet result will look like, from the point of view of a different team studying a different field, sometime in 2026, when the second epoch imaging finally arrives. Recall that Kappa Tauro is the nickname for Sears U100588, the F356W dropout discovered by Marika Gandolfi and her collaborators in the Sears Deep Field, in the constellation Boötes, at coordinates right ascension 14 hours 19 minutes 32.97 seconds and declination plus 52 degrees, 47 minutes, 52.11 arcseconds. The photometric redshift fit, if Kappa Tauro were a galaxy, gives a value of approximately 32, with the universe at that redshift being approximately 90 million years old. That is 200 million years earlier than the current confirmed spectroscopic record holder. It is well inside the era when, according to standard galaxy formation models, even the most efficient star formation would not have had time to assemble structures bright enough to be detected. By 2026, 3 competing interpretations of Kappa Tauro had crystallized in the literature. Each had a paper or papers behind it. Each had a research group advocating for it. The interpretations were not in opposition so much as they were in suspension, waiting for the decisive measurement that would resolve which one was correct. The first interpretation was that Kappa Tauro is what it appears to be on the dropout method's terms. It is a galaxy at redshift 32, the most distant galaxy ever observed, formed somehow in the first 90 million years of cosmic time through processes that we do not yet fully understand. The advocates for this interpretation argued that the photometric fit, while extreme, was not impossible, and that lensing magnification from a foreground galaxy could account for some of the unexpected brightness. Jung, Somerville and Ear published a paper in 2025, Archive 2504.18618, that argued the standard cosmological model is not actually broken at redshifts 12 through 30, even given current observations, and that the apparent abundance of bright early galaxies could be accommodated within model uncertainty if you're careful. The galaxy interpretation of Kappa Tauro fits inside this argument. The galaxy interpretation is still alive. The second interpretation was the one that gained ground after the Bullet BD result. Kappa Tauro is an ultra-cool Y-class brown dwarf in our own galactic neighbourhood, hiding in the Sears field, masquerading as the most distant galaxy ever observed because of the methane and water break in its atmospheric spectrum mimicking the red-shifted Lyman break. The Gandolfi 2026 A&A paper, A&A706, A364, RCIV 2509.01664, presented careful fits using the Sonora Cholla and Atmo 2020 model grids. The fit suggested a Y2 or Y3 brown dwarf at an effective surface temperature between 300 and 400 Kelvin, distance between 127 parsecs and 1800 parsecs. The probability of detecting such an object in the Sears volume was small, about 2% for a Y2 and about 1% for a Y3, but not absurdly small. The Heinlein 2026 paper independently confirmed the photometric fit, calling Kappa Tauro very likely an ultra-cool Y dwarf. The third interpretation was the most exotic. Andrea Ferrara and his collaborators in 2026, and a separate group led by Myung-Won Jeon also in 2026, proposed that Kappa Tauro could be a pair instability supernova at redshift around 15. A pair instability supernova is the final explosive death of a very massive primordial star between approximately 140 and 260 solar masses, in which the unstable production of electron-positron pairs in the star's hot core causes the loss of pressure support and triggers a runaway thermonuclear reaction that detonates the entire star. The remnant is nothing. The light curve has a characteristic shape, with a long, slow decline over weeks to months in the rest frame, stretched to years by cosmological time dilation if the event is at high redshift. The Ferrara and John models suggested that a pair instability supernova at redshift 15 could produce a spectral peak in the F444W filter, consistent with what was being observed. The interpretation was speculative but physically motivated. It is the kind of object that has been theoretically predicted for decades, but never confirmed observationally. If Kappa Tauro turned out to be a pair instability supernova, it would be the first one ever directly detected. These three interpretations cannot all be correct. The data, when fully analysed, will pick one. The decisive test for Kappa Tauro, as for Bullet BD1 and Bullet BD2, will be proper motion. A galaxy must have none. A brown dwarf at 100 parsecs will have 100 or more milliarc seconds per year. A brown dwarf at 1000 parsecs will have 5 to 10 milliarc seconds per year. A pair instability supernova at redshift 15 will have none and will additionally show a fading or evolving light curve over a multi-year baseline. The current proper motion upper limit from the existing 2.3-year imaging baseline of Sears is approximately 0.137 arcseconds per year, which is not yet precise enough to distinguish between a distant brown dwarf and a stationary extragalactic source. A new multi-epoch JWST campaign is needed to push the proper motion precision down to the few milliarc second level that would settle the question. The JWST queue for 2026 contains the additional observations. The data is expected to begin arriving by the late summer or early fall of 2026. The community is waiting. The team that will make the measurement is, at the time this video is being recorded, somewhere out there preparing for it. Imagine, if you will, standing inside the JWST observation queue on the night the second epoch image of Kappa Tauro is finally collected. The telescope is parked at L2, 1.5 million kilometers from Earth, in its slow orbit around the second Sun-Earth Lagrange point. The mirrors are pointed at Bootas, at the small patch of sky that contains Sears U100588. The integration is running. Photons are arriving at the detector at a rate of perhaps a few per second from the faint red point of light that is Kappa Tauro. The signal is being recorded. The data will be downlinked to Earth in a few days. The processing pipeline will run. The astrometric registration will be performed. The comparison with the existing imaging will be made. The pixel that contains Kappa Tauro will either be in the same place it was 3 years ago, or it will be slightly to the side. If it has not moved, we are looking at one of the most extraordinary objects in the history of cosmology. Either a galaxy at the dawn of time, more remote than any galaxy ever spectroscopically confirmed, or a pair instability supernova that brought a primordial massive star's death directly to our eyes. Both of these alternatives are remarkable. Either would be a discovery, either would change something. If it has moved, we are looking at a 1 in 1,000 fluke that has held the attention of the cosmological community for 2 years. A Y-class brown dwarf so cold, so dim, so red, so distant from the galactic plane that it survived the first-pass filtering of the deep field surveys and ended up in the catalogue of high redshift galaxy candidates. The mythology around Kappa Tauro would deflate. The previous most distant galaxy candidate would slip off the top of the list. The community would quietly absorb the result, update the catalogues, and move on. The corresponding result would be no less interesting for what it teaches us about the failed stars in our galactic neighbourhood, but it would be smaller in headline weight. The current photometric evidence favours the brown dwarf interpretation. The Heinlein 2026 paper and the Gandolfi 2026 A and A paper both came to similar conclusions on the photometric grounds. But photometry is not enough. The community has learned, through the Bullet BD experience, that photometric chi-squared comparisons are not decisive, that brown dwarf and galaxy templates can both be fit to faint dropout data, and that proper motion is the test that actually settles the question. So we wait. The data is in the pipeline. The most distant thing in the picture might also be the closest. That phrase, which began as a metaphor when Kappa Tauro was first introduced, has become the active question. The proper motion test will resolve it. For now, in the spring and summer of 2026, Kappa Tauro is the unfinished corner of this story. The Bullet BD1 and Bullet BD2 have been resolved as brown dwarfs. The systematic contamination at the 1 in 1,000 level has been demonstrated. The methodology for distinguishing brown dwarfs from genuine high-Z galaxies has been developed. But Kappa Tauro itself, the prototype case that started this entire investigation in early 2024, has not yet had its proper motion measurement completed. We are still waiting to find out which of the 3 interpretations is correct. The pixel might or might not have moved. The community will know soon. Part 11. What it means that the boundary is fuzzy. If we step back from the technical details and the case studies and the specific objects in the specific fields, The deeper lesson of this story is about boundaries. It is about how clean a distinction we thought we had drawn between the local universe and the distant universe, between the present and the deep past, between the galactic neighbourhood that contains the Sun and the cosmic dawn of the first galaxies. The lesson is that the distinction is fuzzier than the textbooks have always suggested, and that the fuzziness is not a flaw in our measurements, but a property of the universe itself. The cosmic distance ladder is the conceptual scaffolding by which astronomers infer how far away things are. The bottom rungs of the ladder are well calibrated and reliable. Trigonometric parallax, the apparent shift in position of a nearby star against the background of more distant stars as the Earth moves around the Sun, gives us direct distances out to a few thousand parsecs. Standard candles like Cepheid variables and Type Ia supernovae extend the ladder out to hundreds of megaparsecs. The recession velocity of distant galaxies combined with Hubble's law gives us distances at cosmological scales. Each rung of the ladder is calibrated against the previous one. The whole system has been refined for a century, and at this point the distance to most galaxies in the sky is known to within 10 or 20%. What the bullet cluster brown dwarf story reveals is that one of the ladder's basic assumptions, that we can clearly distinguish foreground from background, has an edge case. The assumption holds almost always. Most stars in any deep image are clearly foreground stars. Most galaxies are clearly background galaxies. The two populations have different colours, different spatial distributions, different responses to multi-band photometry. The few cases where the distinction blurs, where a nearby object can be mistaken for a distant one, are usually obvious in retrospect once additional data arrives. The Y-class brown dwarfs at the edge of the high Z catalogues are not obvious. They were not identified for the first decade of JWST operations. They required follow-up spectroscopy and multi-epoch imaging to be distinguished from the most distant galaxy candidates the telescope was designed to find. They are sitting in the same fields as the real high Z galaxies. They produce nearly identical broadband fingerprints. They differ only in measurements that require time and effort to obtain. The cosmic distance ladder, in this corner of the sky, has been quietly contaminated by an unrelated population that was only discovered to exist in significant numbers after the fact. The JWST broke cosmology headline of 2023 and 2024 was always partially a misreading. The early extreme high Z candidates that produced the dramatic headlines were a mix of genuine breakthrough discoveries and unrecognized brown dwarf contaminants. The cleanup that has been happening since 2025 has been quietly reducing the apparent tension between observations and cosmological models. Some of the candidates that produced the most dramatic headlines have been reclassified as brown dwarfs. The remaining real high Z galaxies, including JD's GZ140 and MOMZ14, are real and remain spectroscopically confirmed records. They are still surprising in their abundance and their brightness, which is one of the legitimate open questions in galaxy formation today. But the apparent Z30 and Z32 candidates that fueled the most extreme version of the cosmology as broken narrative have, in some cases, turned out to be local brown dwarfs. The lambda cold dark matter model is doing better than it appeared to be doing 2 years ago. This is the recalibration. The universe is still strange, but the strangeness has been redistributed. Some of the strangeness that we attributed to the very early universe has turned out to live, instead, in our own galactic neighbourhood. The Milky Way contains failed stars old enough to be approaching the age of the universe, cold enough to mimic galaxies at the dawn of time, and abundant enough to contaminate the deepest catalogues ever assembled. The strangeness did not disappear. It moved. Sit with this for a moment. The picture you have been carrying around in your head, perhaps without ever articulating it, is something like this. There is the Milky Way, our home galaxy, containing the sun and the stars you can see at night, and a vast invisible population of cold objects and dark matter and dust. The Milky Way is, in this picture, a kind of bright local landscape, bounded by its outer edges and surrounded by the much vaster cosmic emptiness. Beyond the Milky Way, far away across millions and billions of light years, lie the other galaxies, the galaxy groups and clusters, the cosmic web of structure, and the deep emptiness between the strands. At the very furthest reaches, at the edge of the observable universe, lie the first galaxies ever formed, only a few 100 million years after the Big Bang, visible to us as faint red points of light in the deepest infrared surveys. The picture is clean. The local universe is here. The distant universe is there. There is no overlap. What the bullet cluster brown dwarf result tells us, and what the broader JWST contamination work has been telling us for 2 years, is that the picture is wrong in one specific way. The boundary between the Milky Way and the distant universe in our deepest images is fuzzy. There are objects in our own galactic neighbourhood that masquerade as objects at the edge of cosmic time. Not in great numbers, but in numbers large enough that we can no longer assume that any given dropout candidate is a distant galaxy until we have done additional work. The cosmic web is not separated from our local neighbourhood by an unmistakable boundary. The closest things in our sky and the farthest things in our sky overlap in their spectral fingerprints. The map of cosmic distance has a fuzzy region at its extreme end, a fog of foreground objects that mimic background objects, and the only way to see through the fog is to do the careful, slow, multi-year work of spectroscopy and astrometry that the Bradach team did with the bullet field. This is a small adjustment to the picture, but it is a real one. The boundary is not a wall, it is a fog, and the fog is made of failed stars, drifting slowly through our own galaxy, having been there the whole time, waiting to be noticed. The Milky Way is more crowded with quiet things than the textbook pictures show. The cosmic distance map is messier at its furthest reaches than the simplest model suggested. The universe is still strange, but the strangeness has been redistributed, and some of what we thought was at the edge of time is, instead, in our own galactic neighbourhood. The intellectual honesty of admitting this matters. The community could have hidden the contamination problem. It could have buried the reclassifications of previously claimed high Z candidates. It did not. It published openly. It walked back the records that needed to be walked back. It celebrated the brown dwarf discoveries as their own kind of remarkable result. The system of correction works. The headlines of 2024 were partially premature. The slower, more careful work of 2025 and 2026 has reshaped the field. You should feel, listening to this, a kind of soft equilibrium. The universe is not broken. The cosmological model is not broken. The dropout method is not broken. What has happened is that an edge case of the method has been documented. The cross-checks needed to resolve it have been developed, and the catalogues are being cleaned up. The strangeness has been redistributed from a place we cannot reach to a place 100 parsecs from the sun. The strangeness is closer. It has been closer the whole time. We just had not yet looked carefully enough to see it. Part 12. The Cosmic Web Above Your Roof. Sit with this for a moment, in the way only someone listening late at night can sit with a thought. 350 Kelvin. Slightly warmer than a cup of tea left out to cool on a windowsill. The most distant object the world's most powerful infrared telescope has ever pulled out of the bullet cluster field is, when we look closely, the temperature of something you could comfortably hold in your hands without it scalding you. The most extreme galaxy candidate in one of the most carefully studied images of the early universe turned out to be cooler than the inside of your car on a summer afternoon. Cooler than your kitchen oven on its lowest setting, only barely above the temperature at which water boils. The distance is approximately 1600 light-years. The figure 500 parsecs more precisely. That is the distance to the Pleiades, the small bright cluster of stars you can see with your naked eye in winter. The 7 sisters that have appeared in human myths for at least 4,000 years. It is closer than the Orion Nebula. It is vastly closer than the centre of the Milky Way. Bullet BD1 is in the same galactic neighbourhood as the Sun. It is, in cosmological terms, our neighbour. The light it emits crosses 1,600 years of space to reach the James Webb's mirrors. In comparison, the light from a galaxy at redshift 14 has been travelling for 13.5 billion years, an interval 10 million times longer. The proportions are unforgiving. The boundary between near and far that we have been so comfortable with for a century turns out to have a fog of teacup temperature objects sitting between us and what we thought we were looking at. The age of the object is approximately 10 billion years. We cannot measure it precisely, but the temperature gives us a strong constraint. A brown dwarf cools at a rate set by its mass and its initial heat content. To reach 350 Kelvin, a 30 Jupiter mass object needs to have been cooling steadily for somewhere on the order of 10 billion years. That is older than the Sun. The Sun is about 4.6 billion years old. The Earth is younger. The first life on Earth appeared perhaps 3.5 billion years ago. Bullet BD1 was already cooling toward its current temperature for billions of years before the rock under your feet had assembled itself out of the disk of dust around a newborn yellow star. It has been here, drifting through the disk of the Milky Way at thick disk speed of approximately 116 kilometers per second, for as long as the universe has had a Milky Way. It will continue cooling, alone, in the cold dark, for billions of years more, until long after the Sun has consumed its hydrogen fuel and become a white dwarf, and Earth has been engulfed, and the solar system has become something much less recognizable than it is today. Bullet BD1 will outlast all of that, slowly losing its heat to the cold dark around it, drifting through whatever the galaxy has become. This is the object the world's most powerful telescope mistook for the most distant galaxy ever observed. This is the failed star that the dropout method has been quietly miscounting in deep fields, that the Heinlein group has been systematically identifying in JDs and Sears, that the Braidach team caught with a year-long patient measurement campaign in the Bullet cluster field. The strange dignity of the discovery is that the object is not less remarkable for not being a galaxy. It is more remarkable. It is a fossil of an early Milky Way star formation episode, cooling toward thermal equilibrium with the interstellar medium, sitting in our own neighbourhood, having been here the whole time. The universe contains objects this strange. They share our galactic neighbourhood. They have been doing so for billions of years before any of us were born, before the Sun was born, before the Earth was born. The lesson is not that the dropout method is broken. We discussed this. The lesson is not that the cosmological model is broken. The lesson is that the universe sometimes speaks in accidental homonyms, and the work of astronomy is to learn to tell them apart. Two completely unrelated kinds of objects produce the same fingerprint in our broadband photometry. One is at the edge of the observable universe, the other is in our galactic backyard, and from the outside they look the same. The cosmic distance map has a fuzzy region at its furthest reaches, made of cold local objects that masquerade as the most distant things in the sky. The map can be refined, the fog can be cleared, but only with the careful, slow work of multi-epoch imaging and high-resolution spectroscopy. The cleanup is ongoing in 2026. The cleanup will continue. What this should leave you with, as you settle into the quiet of whatever room you're listening in, is not a sense of loss. The early universe has not been taken away. The real spectroscopically confirmed records, JD's GS-Z14-0 at redshift 14.32 and MOM-Z14 at a comparable redshift, remain in place. The cosmic dawn is still being mapped. The first galaxies are still being found. What has changed is that some of the candidates that looked like the very most extreme records have, on careful inspection, turned out to be cold local objects in our own galaxy. The cosmic dawn is still real. The candidates that survive the cleanup are real. The dropout method, with the cross-checks now in place, will continue to be the workhorse of high redshift galaxy science for as long as we have infrared telescopes in space. What this should also leave you with is a sense of how full the Milky Way is. The galaxy is not a sparse landscape with a few 100 billion stars scattered across 100,000 light-years of disk and halo. The galaxy is instead a crowded place, with stars and brown dwarfs and free-floating planetary mass objects and clouds of gas and dust and dark matter, all woven into a structure we're only beginning to map. The brown dwarf population, hidden from previous telescopes because the objects are too faint and too cool to detect, with anything less sensitive than the James Webb, is comparable in number to the low-mass star population. The galaxy contains tens of millions or hundreds of millions of failed stars drifting slowly through the disk, cooling steadily over billions of years, occasionally being noticed by a careful astronomer with the right equipment and the right patience. Bullet BD1 and Bullet BD2 are two of them. They are not the only two. They are probably not even close to being among the most interesting two. They are just the two that, in early 2026, the Bradach team happened to catch in the act of pretending to be the edge of the universe. If you go outside tonight on a clear dark night away from city lights, and you look up at the sky, you will see thousands of stars with your naked eye. You will see, if you know where to look, the band of the Milky Way arching overhead. You will see, if your sky is dark enough and you are patient enough, the faint smudges of distant galaxies. What you will not see, with any telescope you can buy, with any unaided observation, are the thousands or millions of failed stars in our galactic neighbourhood, cooling silently in the dark. The James Webb sees them, in 2s and 3s, in the deepest infrared images ever taken. Most of them are too faint even for the James Webb. The galaxy is full of quiet things that we cannot see and that we have been overlooking for as long as we have been astronomers. The bullet cluster brown dwarfs are a small reminder of that. The cosmic web above your roof contains, at any given moment, a vast number of cold, dim objects that the brightest telescopes ever built can barely detect. Some of those objects, at this moment, are masquerading as the most distant galaxies ever found in catalogues assembled by the most careful research teams in the field. Some of them will be identified in the coming years through the same combination of spectroscopy and multi-epoch imaging that resolved the bullet field. Some will continue to drift quietly through our deep field images, undetected, uncatalogued, contributing photons to images that are nominally about the early universe, but in fact contain quiet local things mixed in. The map of cosmic distance has in this corner a permanent residual uncertainty that we will only ever be able to reduce, never eliminate. The closest things and the farthest things, in some small but real way, will continue to look the same, because the underlying physics that produces their broadband spectral signatures, while unrelated, leaves indistinguishable fingerprints in our best low-resolution data. The phrase that the bullet team kept coming back to, half metaphor and half active suspicion, was that the most distant thing in the picture might also be the closest. We have learned, over the course of this story, that the phrase is not metaphor. It is sometimes literal. The most distant thing in a JWST broadband image, the faintest red point with the cleanest dropout signature, can turn out to be a 500 parsec away brown dwarf, drifting through the disk of our own galaxy, the temperature of a cooling cup of tea, older than the sun. The phrase has, in this story, become a true statement about the structure of our deepest images. It is no longer a worry. It is a fact about how the universe presents itself to us at the extreme edge of what we can measure. There is a kind of soft existential weight to this. Some of the dots we have been calling the first galaxies are, in fact, ancient cold fossils inside our own neighbourhood. They are not at the dawn of cosmic time. They are not at the edge of the observable universe. They are instead drifting at thick disk speed through our own galactic disk, having done so for as long as the sun has existed and longer. The picture of where the universe begins and where our galaxy ends is fuzzier than the textbooks have always suggested. The boundary is not a wall. It is a fog of quiet things mimicking louder, farther things. The boundary is, in this corner of the sky, partially populated by the failed stars of our own galactic history, cooling toward eventual thermal equilibrium with the cold cosmic background. The Milky Way is, in part, a galaxy of failed stars. They have been here the whole time. They have been here longer than the sun. They will be here long after the sun is gone. Some of them are visible to the world's most powerful infrared telescope. Most of them are not. They drift slowly through the disk, doing nothing, costing nothing, communicating with nothing, simply existing, cooling, in the dark. Two answers from the same fingerprint. The phrase we introduced when we were examining the dropout method has, by this point in the story, deepened into something more than a methodological observation. It is a feature of looking itself. Two completely different kinds of objects produce indistinguishable spectral signatures in our best broadband data. The job of astronomy is to add the cross-checks needed to distinguish them. We have learned, with the bullet field result, what some of those cross-checks should be: proper motion, high-resolution spectroscopy, Bayesian template fitting that explicitly compares galaxy and brown dwarf models. The cross-checks are not new tools, they are the standard arsenal of careful work. What is new is that we have learned, through the bullet cluster experience, that those cross-checks are sometimes necessary even for the most extreme high-Z candidates in the deepest fields, because two answers can come from the same fingerprint, and only the cross-checks tell us which answer is right. So when you next look at an image of the early universe in a news article, or a popular science book, or a documentary, and you see a bright spot labelled as the most distant galaxy ever observed, take a moment to remember the bullet cluster. Remember that two of the most exciting high-Z galaxy candidates of 2025 turned out to be ultra-cool brown dwarfs in our own galaxy at 500 parsecs from Earth, cooler than a kitchen oven, older than the Sun, drifting quietly through the galactic disk. Remember that Capitaro, the prototype case from 2024, may turn out the same way when its proper motion measurement is completed in late 2026. Remember that the cosmic distance map has a fuzzy region at its furthest reaches, and that the only way to clear the fog is the careful, slow work that the Bradach team modelled for the rest of the field. The most distant thing in the picture might also be the closest. The phrase, which began as a working principle in a small office at Ljubljana or Davis in early 2025, has become a closing meditation on what it means to look at the sky. The cosmic web above your roof contains many quiet things. Some of them are very far away. Some of them are very close. From the outside, in low-resolution broadband photometry, they can be hard to tell apart. The work of astronomy is to tell them apart. The work goes on. The map of cosmic distance is being refined. The hidden population of failed stars in our galactic neighbourhood is being mapped, one by one, in the deepest JWST fields. The first galaxies are still being found. The cleanup is still underway. And on a clear dark night, when you look up at the cosmic web, the picture in your head should be a little softer at its edges than it used to be. There is no hard wall between our galaxy and the early universe. There is a fog of failed stars between us and the cosmic dawn, and some of them are 1,600 light-years away, cooler than a cup of tea, older than the Sun, drifting slowly through the disk of the Milky Way at the speed of the thick disk population to which they belong. They have been here the whole time. They will be here long after we are gone. They are not what we thought they were. They are in some way stranger and more wonderful than what we thought they were. They are not at the edge of the universe. They are in our backyard, and the most distant thing in the picture, by an accident of physics that nobody chose and nobody planned, might also be the closest. That is the lesson. That is what the bullet team found. That is what no one was ready for. The cosmos has been speaking in accidental homonyms, and we are only just learning to hear the difference. Sleep well. The galaxy is full of quiet things. They are not going anywhere. Part 12 continued. If you have stayed with this story all the way through, you have followed a journey that began in a control room in late January of 2025 and ended at the cosmic web above your own roof in the present moment. The interval between those 2 points contains an enormous amount of scientific work. The Bradach team's patient year of waiting, the NIRSpec follow-up campaign, the second epoch NIRCam imaging, the proper motion measurement, the chi-squared fits, the careful cross-checks against brown dwarf templates and galaxy templates, and pair instability supernova templates. the parallel work by Heinlein's group on the broader JD's contamination problem, the Capotaro case still hanging in the air, the community's quiet acceptance in the spring and summer of 2026 that some of the most spectacular high-Z candidates ever found were not what they had appeared to be. None of this work was loud. None of it broke headlines in the way the original false discoveries did. The cleanup, like all good cleanup work, was patient and slow, and largely uncelebrated. That is, in some ways, the deeper meaning of the story. The most consequential work in modern astronomy is often the cleanup work, the careful, slow auditing of previous claims, the patient construction of cross-checks, the willingness to walk back a record when the evidence demands it. The bullet cluster brown dwarf result is a small but important example of that kind of work. The team had 2 faint red points in a heavily lensed field. They had a dropout signature that would have justified a claim of 2 record-breaking galaxies. They chose patience instead. They obtained the spectroscopy. They scheduled the second epoch. They waited a year. They did the careful work. The result, when it came, was not what they had hoped for in the most dramatic sense, but it was what the data actually showed. The most distant thing in the picture turned out to be one of the closest. The team published openly. The community absorbed the result. The catalogues were updated. The work goes on. What you should carry away with you from this video, as you drift toward whatever comes next in your evening, is not a sense that anything has been broken or taken away. The early universe is still being mapped. The first galaxies are still being found. The dropout method, with the cross-checks now in place, will continue to be the workhorse of high redshift galaxy science. Nothing has been lost. What has been gained is a more honest picture of how the universe presents itself to us. The boundary between near and far is fuzzy. The fog at the extreme edge of the cosmic distance map is real. The fog is made of failed stars in our own galactic neighbourhood. They have been there the whole time. They have been there longer than the sun. They will be there long after we are gone. The James Webb has begun to see them, in 2s and 3s, in the deepest infrared images ever taken. The Milky Way is in part a galaxy of failed stars. The phrase has come back several times in this video, and each time it has been earned by a slightly different set of evidence. We earned it first when we discussed the Heinlein 2026 population estimate, which suggested that the total brown dwarf population in our galaxy is comparable to or greater than the population of low-mass main sequence stars. We earned it again when we walked through the cooling timescales and realised that a 350 Kelvin brown dwarf is roughly as old as the universe itself, a fossil of an early Milky Way star formation episode that has been quietly cooling for 10 billion years. We earned it once more in the bullet field, when 2 of those fossils turned out to be hiding in the same image that contains the most carefully studied dark matter signature in the sky. The phrase is not poetry. It is, at this point in 2026, a description of what our galaxy is. Sit with that for a moment. The galaxy you live in is, in part, a slow accumulation of cold, dim objects, dropped out of the star formation process billions of years ago, drifting quietly through the disk and the halo, occasionally being noticed when one of them passes close to a piece of equipment sensitive enough to detect it. Most of them will never be catalogued. Most of them will never be studied. They will continue cooling, alone, in the dark, for as long as the galaxy lasts and longer. The picture you carry around in your head of the Milky Way as a sparkling sea of stars is, in this small but real way, incomplete. There are many more quiet things than bright things. The bright things are the ones we can see. The quiet things have been here longer. 2 answers from the same fingerprint. We introduced the phrase when we were examining the dropout method. By now, it has become more than a methodological observation. It is, in a real sense, a feature of looking itself. Our best instruments produce data that, at the extreme edge of what we can measure, cannot fully distinguish between 2 completely unrelated kinds of objects. The brown dwarf methane and water break and the red-shifted Lyman break of an early galaxy are accidental homonyms in the language the universe speaks to us through its photons. The job of astronomy is to learn the difference. The bullet cluster story is one small chapter in that learning, There will be more. The most distant thing in the picture might also be the closest. This phrase, which began as a working principle in a small office at Ljubljana or Davis in early 2025, has by now become a meditation on what it means to look at the sky at all. The cosmic web above your roof contains, in its deepest detail, a fog of teacup temperature failed stars that the James Webb has only just begun to detect. Some of them mimic the most distant galaxies ever found. Most of them are too faint to be detected at all. They have been here the whole time. The boundary between our galactic neighbourhood and the cosmic dawn is, in the deepest infrared sky, partially populated by quiet local things that look like loud, far things. The map of cosmic distance has a fog at its furthest reaches. The fog is real. The fog can be cleared slowly with patient work, but the fog will never quite go away, because the underlying physics of methane absorption and hydrogen blanketing happens to leave overlapping fingerprints, and no amount of work will change that fundamental fact about how light interacts with matter at these particular wavelengths. This is what no one was ready for. The Bullet team was looking for the most distant galaxies ever found. They found, instead, two of the coldest and most ancient failed stars our galaxy contains. They found a tear in the simplest picture of cosmic distance. They found that two completely unrelated kinds of objects can produce the same fingerprint in our best data. They found that the boundary between the early universe and our own galactic neighbourhood, at the extreme edge of what we can measure, has a fog of quiet things that we cannot easily see through. They published the result. The community absorbed it. The cleanup is underway, and so, on a clear dark night, when you look up at the sky and the cosmic web is faintly visible above you, the picture in your head should be a little softer at its edges than it used to be. Some of the dots you see, and some of the dots you do not see, are not what they appear to be. The most distant things in the picture might also be the closest. The galaxy is full of quiet things, drifting through the disk at thick disk speed, cooling toward the eventual thermal equilibrium with the cold cosmic background. They are not going anywhere. They have been here longer than the sun. They will be here long after we are gone. They are, in some small and quiet and wonderful way, our companions in this corner of the galaxy, even though they will never know about us and we will, for the most part, never notice them. Sleep well. The cosmic web above your roof is more crowded than you thought. The boundary between near and far is fuzzier than the textbooks suggest. The most distant thing in the picture might also be the closest. The galaxy is full of quiet things. They are not going anywhere.